everyone, today I'm back with the sixth part of our series Biomedical Image Analysis, and we are gonna be learning about transforming images, so basically rotating them, shifting them, and also to learn how to resample, which is downsampling or upsampling, and we'll learn which interpolation we should use and which interpolation gives us the best results, but also we'll learn about some time disadvantages, and this will be today's topic. Let's start with the affine transformations first. So affine transformations manipulate images while preserving geometric properties like straight lines and parallelism. And four common affine transformations are translation, which shifts an image along the x or y axis, rotation, which rotates an image within its plane, scaling, which changes the image size, and shearing, which skews the image by distorting its axis. And for this section, I'm gonna be using brain images from the OASIS dataset. I'm gonna be using moderate demented brain images. So let's start by shifting an image so that the brain is in the middle. And for that, we are gonna be using the center of mass, which will make our jobs really easy because we'll calculate the middle of the image and then find the center of mass of the image. So basically the brain center of mass, so that we can take the difference and know how much we will need to shift our image. So let's start. Image file. In my article, I've used two different images. One was little bit like this, so I needed to rotate them to make it normal. One was shifted, but now I found an image that is both shifted and rotated, so I'll use it for both of these transformations. InJio, then import SciPy, BI, then let's take the what should I name it? May be transformed or augmented. Transform this. Let's take the transform. In the shape of the image. These images have 3 dimensions. They have the color channel too, which might make our jobs hard, so I'll teach you how to turn them to grayscale too. So let's calculate the center of mass. BI dot center of mass. And you have two options here. So because shifting will shift the color dimension, so it will be a really strange image. You can try it yourself. So you can either take the mean of the image and take its center of mass to shift it, and then while shifting it will give 0 to the color dimension. Or I'll also show you how to turn it into grayscale so that you don't have to do all of these. But I wanted to show you both ways. So we'll take the mean and then print center of mass. Let's calculate the 0, how much we need to shift it, the 0th dimension. So with this, we have calculated the middle of the image in the 0th dimension. So basically x-axis, and then taken the center of mass and subtracted from it. Did I make an error here? Sometimes gives this, okay. And then we have the D1. I don't even need to do this. You can do it too. And then we have the D1 shape 1 divided by 2 and subtract the center of mass in the y direction. Okay. So now we'll shift our image, say ndi.shift, give our image, and we'll shift it D0, D1, and we'll have to give 0 so that it doesn't shift the color channel. And then I'll plot both of them like normal one and the rotated one, or I can actually show three of them because when we shift it, it won't um, be normal because it's also rotated. That's the problem. So I'll have to show you both to see for you to be able to see the shift. Plot 3, 0 dot aim show. Let's first show the normal one. Image, CMake gray. Let's also give it a title. Normal image. Can either do it with a loop for x and axis dot off, but let me also show it to you to do like this time. Just on that game show shifted. Oh, let's first show the transform, not transformer. And this is the image. I'll have to say that this is the transformed, and then this is the transformed. This will stay, and I'll quickly also read the normal image. This one that I am sure. Will also show the shifted one. Then I can shift that. Okay. Now I can show it. But after changing the title, let's shift the image. See. Okay, so the shape of our image is 190 by 200, and we have the color channels RGB, and then center of mass is this point. And as you can see, the original image was a little bit close to the side, but it's now right in the middle, like this. So it has been shifted to the middle, which is really nice. And after we rotate this, it will really look like this normal image. So let me show you how to rotate it, which is also really simple because gonna call ndi.rotate, and I'll just rotate the shifted one. Or I can also wait, do it here basically. I think that's better. Rotated ndi.rotate, shifted, and then we specify the angle. Can give -10 maybe. And we have to definitely say reshape both, because if we don't do that, it will basically turn the whole image and it will have black areas here, like it will again put a frame on top of the, like around to rotate the image, so the shape will change. So basically we are saying don't change the shape, just rotate it, and then it's the same image. So that's really important to not forget. And I'll do 4, and we can say existing that and show rotated CMake gray. This 3 dot set title rotate the image axis 3 dot axis off. And here you can see that it's completely normal now because we've shifted and rotated them. And this was a great example. So after this, let me show you how to do affine transformations with custom matrices. First, just to show you an identity matrix, I'll use that to transform the image and nothing will change because we will get an identical image with, we get an identical image with an identity matrix. So I thought of writing it again, but I'm too lazy for that. Okay. Let's say transform in the I dot affine transform. We'll give the image, let's give the rotated one for example, and then the matrix. Then let's show them together as two subplots. But I'm thinking if I should continue this. I think that would be better. Take this. We here. Let's say instead of transformed identical, we transform rotate. Can't even see rotated matrix, and then 5 identical CMap play access4 dot set title rotated image transformed with entity matrix. I also have to change the at this point the figure size because it will overlap. Maybe 12 by 6. Let's see. And then access 4.xo. And let me show you the other metrics too. So this will basically translate and rescale the image in matrix 2. And then say maybe rescaled I.affine transform identical match to, and then we'll give 6 subplots if show rescaled CMap way this 5 dot set title rescale and image that says oh. Now let's see. Here you can see the, should we make 15 by 12? Oh, still just to, that's I can say an identical image because you know it. So 18 by 15. Here you can see the problem. It also translates and rescales the color channels too. So that's the big dimension if the image has a color channel. For that, what we can do is we can convert it to a grayscale image. I was gonna show it to you in the like a little bit later, but I'll show it to you now. So what we do is say gray is the mp dot. We have a formula for this. Say 3, and then we move we take the dot product this basically, and now it should be fine. Let's see. Oh, did I make it wrong? Let me see. It's so amazing of me to forget to write the image here. Now it should solve the problem. As you can see, now it works and it rescaled and translated the image. So this was a good exercise. After this, we'll talk about resampling. So let me move on to that. Resampling basically creates a like brand new image based on the old one, and different from cropping, the field of view does not change. Instead, the amount of space sampled by each pixel is increased or decreased, which changes the shape of the array. So we upsample it or downsample it. When we downsample it, the information is merged across multiple pixels to reduce the image size, and when we upsample it, the image shape is increased. But this doesn't like increase the resolution as we don't add new information. This is usually mixed. But one useful application of upsampling is to make the sampling rates along different dimensions equal to make voxels cubic. And that's all. Now let me show it to you. For that, should we use I'm thinking the hard decom, or do we don't need it? I don't think we need it. Let's do it. Let's continue with the moderate developed images. So what we do is image. Let me take the rotated one. Say rotated downsampled and ndi.zoom rotated and zoom 0.5. And this will basically reduce the number of elements on each axis by half, as you can see here, and downsample it. You can also print the shape downsampled image. And dot shape. Maybe I should continue with the previous one because I really liked how we can see each transformation. Maybe it's not the best idea to put them all in the same row, but as long as we can see it, then we are fine. I'll make it 8 and also add the upsampled one too. Take it up. So here we'll say ndi.zoom. But what we do is we'll give a number bigger than 1. So for example, so this will like double the number of elements in each axis, dimension, sorry. And then shape the upsampled image, rotated up that shape. And I forgot to plot them. So axis 6 dot intro rotated down sampled axis 6 dot set title Let's see. Oops, that was bad. What happened for image data? Again, the problem with grace. I should have said this. Gray and now it should work. Now what's wrong? Oh, I had done it again. Okay, now it should work. And you can see the, oh, this is better. Can I make it maybe 25 by 23? This is better. So here you can see the downsampled and upsampled image. The downsampled seems more blurry and the upsampled seems more sharp, if you can notice it, but it's really hard to notice. So other than that, let's see. Now let's talk about interpolation. So when we resample, we create a new image from an old one, as I mentioned. And this requires estimating data that wasn't originally there because we are either shrinking or making it bigger, like giving more points, and we have some gaps there we need to fill. So this estimation process is called interpolation. For example, if we want to make 10 values to a 100, we need to estimate the values of the points in between. For that, we can use nearest neighbor, which uses the closest measured value. Nearest neighbor interpolation is used a lot, and it's we use the nearest neighbor zero order interpolation. And if we do that, if we like just look at the near values and estimate them, it's a zero order interpolation because we aren't modeling any relationship between the original values. For higher order interpolation, which gives higher resolution, and we'll see it soon, SciPy uses B-spline interpolation, which models space between points with spline functions of a specified order, which is between 1 and 5. And 1 means here that we are like interpolating linearly, and if it's 2, we are interpolating quadratically. If it's 3, cubically, and it increases like that if when we increase the order, and it gives us a better gradient, better resolution like that. And let me show it to you now. So for that, we'll take an array and make it a 10 by 10 array. Say 10, 10. For that, we'll show it with reds. Or plt dot show. Let's give it a title. Say image. So now here you can see the original image. Now we are gonna resample it and see what happens, but with different interpolations. pi dot zoom, image zoom 10, and I'll make it very dramatic for us to see the effect. Because if we zoom a lot, like if we upsample it a lot, then we need those estimations to be precise, and it will be really pixel by pixel if we don't use a good interpolation, like a zero order interpolation. Zoom 2, zoom, image, zoom 10, order 2, zoom 3, zoom, image, zoom 10, order 4, and then big axis. Yeah, so that's soft roads to 2. Now let me show this to you first, starting from the original image again. And then CMap reds, of course. and zero order interpolation. Finally, we are done. Now let's see. And here you really see the difference. With order zero interpolation, we see the pixels, like even the lines. But with order two interpolation, it's kind of better. With order 4 and order 2, we don't really see the difference, but with order 4, we have even more resolution and even more kind of smooth gradient. So the only disadvantage is computational time. So it's really hard to do fifth order interpolation for a 3D volume, which can take very, very long time to calculate. So I'll also show you this example in the brain image and how it will change it. So let me do that too. Yeah, that's zoom. Let's take the gray one. We'll zoom it 4 times, order 0, then up 5. Let's zoom gray from zoom 4 in the order 5. So let's take a specific part of the image and show that so that we can really see the difference. 0. We have, let's see, 90 to 200. This, let's say, maybe 60 to 20, 60 to 120. I think that's better. Or even 150. Okay. This one, but I am sure. So here you can see the original shape and the upsampled shape. Oh, I think with the upsampled we could have forgot it. Oops. Because we don't see anything with this, just a pixel. So I forgot the CMap grade. It automatically shows it with your varieties library, I believe. Yeah, this is better. AC map play. Oh no, not that. Play. Oops. And now you can see how pixeled this is and how smooth that is. This really shows the dramatic difference too. So this was all from the sixth part. In the next video, which will be our last video, we'll talk about comparing images, basically calculating how different they are using mean, absolute error, and intersection of union. And we'll also learn about how important normalizing measurements is, because they really change if the result is statistically significant or not. So stay tuned for that, because we'll also get into some statistics and some interesting and good looking quotes. And see you there. Bye.